In this video, we're going to take a look at ideal gases and real gases and see how they compare. We'll explore the ideal gas law and then talk about how sometimes gases deviate from this ideal gas and actually behave differently in certain conditions. So the ideal gas law is PV equals nRT. And each of the variables represent the following. So pressure is capital P, and that's measured in kilopascals. Little n is the number of moles. V is the volume in liters or decimeters cubed. And then R is the gas constant, and that is equal to 8.314 decimeters cubed times kilopascals per mole Kelvin. And temperature is measured in Kelvin. So in our first example, we're being asked to find the molar volume of a gas at standard ambient temperature and pressure. So what that is 298 Kelvin and 100 kilopascals. So we'll solve for that. So we write PV equals nRT, but we need to find volume, so we'll rearrange that. So V equals nRT over P. So we need to make sure that our units are in the right format. So first of all, we have kilopascals and Kelvin, so those are fine. So we want to know the molar volume of a gas at standard ambient temperature. So it would be, the moles would be 1 mole times the R value, which is 8.314 kPa decimeters cubed mole Kelvin times 298 Kelvin all over the pressure, which is 100.0 kilopascals. That is equal to 24.8 liters per mole. So every mole of a gas, again, remember all gases are the same. They have the same number of particles at a specific volume. So 1 mole of a gas at standard ambient temperature and pressure is 24.8 liters per mole. So our next example, we can use the ideal gas law and then find out the moles of nitrogen to find out the mass of nitrogen in 1 liter. So it says find the mass of nitrogen in 1 liter at 12.5 degrees Celsius and at 126.63 kilopascals. So first off, we put our equation PV equals nRT. We want to know, first of all, moles, so we can rearrange that to PV over RT equals the moles, and then solve. We also need to convert our temperature to Kelvin, so we will add our 273 to the 12.5, so that is 285.5 Kelvin. So now we can solve. So N is equal to, we'll just switch it to the other side, 126.63 kilopascals times 1 liter over 8.314, I'm not going to write the units, times 285.5 Kelvin. So we find out that we have 0.0533 moles of nitrogen gas. Now that we have our moles of nitrogen, we can find out our mass of nitrogen using our the number of moles is equal to the mass over the molar mass. So if we multiply by the molar mass, we'll find out the mass. So the mass of nitrogen is equal to the moles times the molar mass. And remember, nitrogen gas is a diatomic molecule, so 2 times 14.01 equals 28.02 grams per mole. and we had 0.0533 moles times the 28.02 grams per mole. So that is equal to 1.494 grams. But our original question was in 2 sig figs, so it would just be 1.5 grams. So that's what the mass of nitrogen gas is in 1 liter of gas at those conditions. So far in our gas unit, we've been talking about ideal gases, meaning that gases are behaving in a particular way, but real gases in real life will not always fit the ideal gas law criteria. In certain instances, they will deviate from the expected values. So gases perform best in the ideal sense when they're at low pressure and high temperature, and they deviate away from there. And you can see this here. There is some deviation. Ideal gases should behave this way without much change, but when you deviate the temperatures and so on, they sometimes misbehave. So under high pressure, the particles will be close enough together for intermolecular forces to actually impact them. We said before that they are not impacted by intermolecular forces, that all their attractions, there's no forces of attraction or repulsion, and all of their collisions would be elastic. That's not always the case. Under high pressure, they will be close enough together that those intermolecular forces will impact them. And then at low temperature, the molecules will be moving much more slowly, and the molecules would be closer together because of the intermolecular forces. So intermolecular forces will impact them. And in those cases, the gas molecules will be attracted to one another. So they won't behave the same way as in the ideal gas. Also, different gases will be different, so and they'll deviate more so from the ideal gas law. So gases that are polar will deviate more than gases that are nonpolar because of those intermolecular forces. So you just have to understand that in certain conditions they are not ideal.